Hi, this is Jeff Heen. Welcome to Applications of Deep Neural Networks with Washington University. In this video, we're going to look at transfer learning with Keras for computer vision. There are a ton of state-of-the-art neural networks out there that you can transfer the weights in and then fine-tune them for your own applications. In this video, we're going to see how to do just that. So the link to this notebook is in the description of the video. I am going to go ahead and open it in Colab. This allows me to actually run the code. So in this example, we're going to take a look at computer vision with transfer learning. And that's really, computer vision and natural language processing are the two things transfer learning are really often used for. What we're going to do here is train a neural network to recognize the cats versus dogs data set. The cats versus dogs it's a Kaggle competition where you trained a neural network to recognize cats versus dogs. Now, it's from 8 years ago, and this shows you how advanced newer technologies like we're using that were not available when this competition went on. Remember this, the top competitor, what would have it taken you to get a gold Kaggle medal, which are very coveted? You would have to be above about 0.98. So remember that. We're going to take a look at it. These are just all of the various image data sets that you can pull in or that Keras makes available for you. I am going to run this, and we're going to pull down the cats versus dogs data set from TensorFlow. They have it all nice and formatted for you so that you don't have to pull it directly in from Kaggle. And I'll tell you another important thing that they're doing here is it's coming in as a Keras data set. These are useful to use when you want to deal with larger data that would not necessarily work in Colab, because the RAM on Colab is about 12 gigabytes. And it's easy to blow right through that RAM if you don't use the Keras datasets. So it's loading it. We'll fast forward to this. This takes a moment. And you don't need to worry about the warning. In the dataset, there were a few corrupted images, which makes it just all the more realistic. Let's look at what the cats and dogs look like. You can see dogs. The label is 1 for dogs and 0 for cats. The other thing you should notice looking at all of these images is they're different sizes and different aspect ratios. We'll need to deal with that. We're going to make them all 150 by 150. I will also mention that the example that I am pulling this from, I based it on an example by Francois Chollier. He gave an example similar on the Keras website a while back, and I adapted it into my class and made some changes to it to make it more consistent with how I represented some of the class material. So just like Francois, we are going to 150 by 150. Now, it doesn't matter that the neural network that we're attaching it to was not trained at 150. The reason for that is think about how a convolution neural network works. The weights are embedded in a kernel, which is a smaller thing than the image, and it's scanning across the image, building those weights, looking for individual features. That makes it positional invariant so that a feature up here or a feature down here could be recognized. So since there's no weights directly tied to the input resolution in a convolution neural network, if a convolution layer is your first layer, then you do not need to retrain the neural network if you change that to be something, say, 150 by 150. So I resize all of the images in the training and validation set to that. To speed this up, since we're dealing with the prefetched data set, since this is such a large data set, we are going to use the prefetching with a batch size of 10. That'll speed things up, give a performance boost, which is always a nice thing on these big data sets. We're going to put some augmentation into here. That, believe me, this is one thing that was not common back when the Kaggle was ran 8 years ago. We're going to put in 2 augmenters, something that'll flip it horizontally. But let's visualize a few of these. So when we run this, we're dealing really just with that first dog that we flipped We're flipping them back and forth and rotating. You can see some rotation and flipping going on there. Next, we're going to create the neural network. So here, we're going to use the weights from ImageNet. So those are weights that Keras provides for the exception neural network. We're going to have the input shape be 150 by 150 by the 3 RGB colors. We're going to make everything trainable false so that we're not retraining those layers. Now we've ripped off the input layer and replaced it with an input shape that is 150 by 150. We're also going to rip off the final layer so that we can put on just a binary classifier of cat or dog, whereas the original ImageNet had, I think, 1,000 images that it was potentially, image types that it was potentially classifying. We're going to scale everything in the range, the RGB input colors from -1 to 1 instead of 0 to 255. Neural networks like that better. And then we're going to put on a final global averaging pool that takes the three-dimensional tensor that is coming out of the last pooling or max pool or convolution layer and makes it just a vector like the dense layer actually needs. We put on a dropout to reduce overfitting, and we put that final one dense layer on. And now we can create the neural network. We print out the summary of what that neural network looks like, just so that we can see all of the various layers going into it. It's still got tremendous number of parameters, which is common for the exception neural network. It's a big, complicated neural network. We're going to compile it using the Atom optimizer, and we're using binary cross entropy. We're doing from logits because the classification labels are from -1 to 1 in the original training set, so we're matching that. Most of the other classification neural networks you've seen in this class, 0 or 1 for A. Most of the other networks that we've looked at, the data sets for binary classification in this class, were either 0 or 1, meaning a positive or negative class. We train it. I'll skip this because it doesn't take a whole long time, but it takes a few minutes. And we can see that our binary accuracy was 0.9652. Okay, where would have that got us in Kaggle? And let's use the validation accuracy. So 0.9746. 0.9746. We would have been in the very, very high range of the silver medal level. But wait, there's more. We can also fine tune. So what we're going to do with fine tuning is we are going to take the model that we had, but we're going to recompile it because we're going to use a different variant of the Atom optimizer. We're going to use a very, very small 10 to the -5 learning rate, but we're going to allow all of the weights to be modified now. So this is no longer where we're only allowing the final layer to be trained. We're going to let everything be trained. You have to be careful with this because you're going to potentially forget what you transferred from the state-of-the-art neural network. But that's why we set such a low Atom learning rate. So we go ahead and we train it, and notice these validation accuracies. Look, it's getting better and better. It goes up into the 98s, and we're ending up at 0.9819. Believe me, you want to do this fine-tuning step. If you're watching this video to compete in the Kaggle competition for my class, that's definitely something you want to do, because that will certainly help you if you're transferring the weights. So 0.9819, where would have that landed us in Kaggle? Right here in third place. Definitely would have gotten a gold medal. So that shows you what the state-of-the-art has done in terms of these neural network techniques. We didn't do any crazy optimization. We just did transfer learning with image augmentation. Those are the two breakthroughs that we made use of since this Kaggle came out. We're also using a much more modern version of deep learning. I mean, 8 years ago, there was no PyTorch. There was really no TensorFlow. I mean, 8 years ago, there was no TensorFlow. I mean, it was probably being worked on in DeepMind, but it was very, very early. There was no PyTorch. There was Torch. You had to learn the Lua programming language. But there were other deep learning technologies available. This has all improved considerably, and you can see what you could do if you could time travel back in time and compete in Kaggle. Tell you what, if any of you are time travelers, I would really get a kick out of it if you would go back in time and make your team name Hi Jeff. I don't know, just something fun to do if you are a Time Lord. Thank you for watching this video, and if you want to see the other videos related to transfer learning in Keras, please subscribe to my YouTube channel so that you do not miss anything. And if this video was helpful to you, please give me a like. Thank you very much.